Welcome! In this video, we'll dive into a classic and challenging problem number 123, best time to buy and sell stock 3. This problem is all about optimizing profit from stock transactions, with constraints that push your algorithmic skills to the limit. Let's explore the problem statement and break it down step by step. In this problem, you are given an array called prices where each element represents the price of a stock on a specific day. Your goal is to design an algorithm to maximize the profit you can achieve by completing at most 2 transactions. Now, a key point to remember is that you can only perform one transaction at a time. This means you must sell the stock you currently own before you can buy it again. The input will be the array prices, and the output should be a single integer representing the maximum profit you can achieve under these constraints. Let's take a look at an example to understand this better. Consider the first example where prices is 3, 3, 5, 0, 0, 3, 1, 4. The output in this case is 6. Here's why. The first transaction involves buying the stock on day 4, when the price is 0, and selling it on day 6, when the price is 3. This gives us a profit of 3. The second transaction involves buying the stock again on day 7, when the price is 1, and selling it on day 8, when the price is 4. This gives us another profit of 3. When we add these, the total profit becomes 6. Another example is when prices is 1, 2, 3, 4, 5. Here, the output is 4. In this case, you only need one transaction, buying the stock on day 1, when the price is 1, and selling it on day 5, when the price is 5. The profit is 5 minus 1, which equals 4. In the second example, it's important to note that no second transaction is necessary since all the profit can be captured in a single buy and sell operation. Now, let's look at another example. If prices is 7, 6, 4, 3, 1, the output is 0. Here, no transactions can be made because the prices are consistently decreasing every day. This means there's no opportunity to buy low and sell high, so the total profit is 0. Finally, there are a few constraints to keep in mind. The length of the input array, prices, will be at least 1 and at most 100,000. Additionally, each price in the array will be between 0 and 10,000. These constraints ensure that your solution needs to be both time efficient and capable of handling large inputs. Now, let's discuss some important edge cases to consider. First, if the array has only one price, such as prices equals 5, no transactions can be made, and the result is 0. Second, if all prices in the array are the same, like prices equals 3, 3, 3, 3, no profit can be made since there's no price change. Third, for very large inputs, such as when the length of prices approaches the upper limit of 100,000, your algorithm must still perform efficiently within the given constraints. Lastly, in cases where the array has 2 distinct peaks, it's crucial that the solution identifies the optimal transactions to maximize profit. These scenarios highlight the importance of carefully designing your algorithm to handle all possible cases effectively. When tackling the problem of maximizing profit from 2 stock transactions, the brute force approach might seem like the most straightforward option. Here, we would evaluate every possible pair of buy and sell transactions, checking all combinations to determine the highest profit. This involves, for each transaction, finding the best profit by buying on one day and selling on a later day, then doing the same for the second transaction on the remaining days. However, this method quickly becomes impractical because of its time complexity. For every pair of days, we need to repeat this process twice, resulting in n cubed time complexity. While it uses constant space, this inefficiency makes it unsuitable for large datasets, such as those with up to 100,000 days. This approach is simply too computationally expensive to be viable. Recognizing this limitation, we turn to dynamic programming, which allows us to break the problem into smaller, manageable subproblems. The main idea here is to calculate the maximum profit for 2 distinct time periods, one covering the days from the start to a given day, and the other covering the days from that point to the end. This observation lays the foundation for a more efficient solution. To implement the dynamic programming approach, we use 2 arrays to simplify our calculations. The first array, left, I, keeps track of the maximum profit achievable from day 0 to day I using a single transaction. The second array, right, I, does the same for the period from day I to the last day. To populate left, we iterate through the array from left to right, continuously updating the minimum price encountered so far and calculating the profit if we were to sell on that day. Similarly, we populate right by iterating from right to left, tracking the maximum price as we move backward, and calculating the potential profit for buying on that day. Once these arrays are filled, the final step is to combine the results. The maximum profit is simply the highest sum of left, I, and right, I, across all indices. This approach is efficient, with a time complexity of O(n), since we only make 2 passes over the array, and a space complexity of O(n), due to the use of the 2 arrays. However, we can take this even further by optimizing the space usage. The most efficient solution leverages a space-optimized dynamic programming strategy, which eliminates the need for additional arrays. Instead of storing all left and right values, we calculate them dynamically during the 2 passes over the array. In the first pass, as we move from left to right, we keep track of the minimum price seen so far and use it to calculate the current maximum profit for the first transaction. In the second pass, moving from right to left, we track the maximum price while simultaneously calculating the combined profit of the first and second transactions in real time. This eliminates the need for extra space, reducing the space complexity to O(1), while maintaining the same O(n) time complexity. This strategy is particularly well suited for large datasets due to its efficiency and simplicity. By dynamically tracking prices and avoiding redundant calculations, we ensure that the solution is both optimal and scalable. Compared to the brute force and array-based dynamic programming approaches, this method strikes the perfect balance between speed and memory usage, making it the best choice for this problem. To tackle the problem of maximizing profit with at most 2 stock transactions, we need a clear strategy. A transaction consists of a buy followed by a sell, and our goal is to determine the maximum profit achievable from these operations, given the array of prices where prices, I, represents the stock price on day I. The optimized dynamic programming approach breaks this into 2 smaller subproblems. First, we calculate the maximum profit achievable with a single transaction for the subarray from the start to any given day I. Second, we compute the maximum profit achievable with 1 transaction for the subarray from that day onward to the end. Combining these 2 results will allow us to derive the answer efficiently while ensuring we stay within the constraints of 2 transactions. To begin, we calculate the maximum profit for the first transaction. For this, we use an array called left_profit, where each element left_profit, I, stores the maximum profit achievable with a single transaction in the subarray from day 0 to day I. As we iterate through the array, we maintain a variable min_price to keep track of the lowest stock price seen so far. On each day I, we update min_price with the smaller of its current value or the price on day I. Then, we compute the profit we would make if we bought at min_price and sold at the current price, prices, I, min_price. This profit is stored in left_profit, I, as the maximum profit achieved up to that day. For the second transaction, we use a similar approach but work backward through the array. We initialize another array, right_profit, where right_profit, I, represents the maximum profit achievable with 1 transaction in the subarray from day I to the last day. This time, we maintain a variable max_price to track the highest stock price seen so far as we iterate backward. For each day I, we update max_price to the larger of its current value or the price on day I, then calculate the profit by selling at max_price and buying at the current price, max_price, prices, I. This value is stored in right_profit, I, as the best profit achievable from that day to the end. Once we have both left_profit and right_profit, we can combine the results to determine the maximum profit achievable from at most 2 transactions. For every day I, we calculate the sum of left_profit, I, and right_profit, I plus 1, which represents the combined profit of the first transaction ending on or before day I and the second transaction starting after day I. We keep track of the maximum combined profit across all valid days to arrive at the final result. Additionally, we handle edge cases. For example, if only 1 transaction is possible, the result will simply be the maximum value in left_profit. This approach is efficient because it uses 2 passes over the array, 1 forward to calculate left_profit and 1 backward to calculate right_profit. The use of dynamic programming ensures intermediate results are stored, avoiding redundant calculations. This method also works seamlessly for edge cases, such as when the array has fewer than 2 days, where no transactions are possible. The efficiency of this algorithm lies in its complexity analysis. The time complexity is O(n), where n is the size of the input array prices, as we make 2 linear passes over the array, one to calculate left_profit and another for right_profit. The space complexity is also O(n), since we use 2 arrays of size n to store intermediate results. Edge cases include scenarios where the input array is empty or has fewer than 2 elements. In such cases, no transactions can occur, so the function should return 0. Similarly, if all prices in the array are the same, no profit is possible, and the result should also be 0. To illustrate, consider the example input prices equals 3, 3, 5, 0, 0, 3, 1, 4. First, we calculate left_profit. We initialize min_price to infinity, then iterate through the array. On each day, we update min_price and calculate the profit for selling at the current price. This value is stored in left_profit, I. For this example, the final left_profit array is 0, 0, 2, 2, 2, 3, 3, 4. Next, we calculate the right_profit array by iterating backward through the prices. We initialize max_price to -infinity and update it with the highest price encountered so far on each day. For each day I, we calculate the profit from buying at the current price and selling at max_price, storing this in right_profit, I. For the example input, the resulting right_profit array is 4, 4, 4, 4, 4, 3, 3, 0. Finally, we combine the results by calculating left_profit, I, plus right_profit, I plus 1, for all valid I. The maximum combined profit in this example is 6, achieved by buying and selling during the first transaction and then buying and selling again during the second transaction. Thus, the final answer is 6. This solution uses an optimized dynamic programming approach to solve the problem of maximizing profit with at most 2 transactions. The algorithm employs 4 key variables: first_buy, first_sell, second_buy, and second_sell. These variables represent the maximum profit achievable in different states of the 2 transactions. 1. Initialization. We initialize first_buy and second_buy to -infinity because buying a stock is a cost, while first_sell and second_sell are set to 0 because no profit is made at the start. 2. Iterate through prices. For each price in the input array prices, we update the 4 variables in sequence. First_buy, this tracks the maximum profit after the first buy. We calculate it as the maximum of its current value and price, buying the stock at the current price. First_sell, this tracks the maximum profit after the first sell. We calculate it as the maximum of its current value and first_buy plus price, selling the stock at the current price. Second_buy, this tracks the maximum profit after the second buy. We calculate it as the maximum of its current value and first_sell price, buying the stock for the second transaction. Second_sell, this tracks the maximum profit after the second sell. We calculate it as the maximum of its current value and second_buy plus price, selling the stock for the second transaction. 3. Return the result. After iterating through all prices, the value of second_sell represents the maximum profit achievable with at most 2 transactions. The algorithm runs in O(n) time complexity, where n is the length of the prices array, as we iterate through the array once. The space complexity is O(1), since we use only a constant amount of extra space. This makes the solution highly efficient and suitable for large input sizes. Here, we are implementing the solution to find the maximum profit from at most 2 transactions using Java. First, we define a class named solution and create a method called maxProfit that takes an array of prices as input. If the array is null or has fewer than 2 elements, we return 0 since no transactions can be made. Next, we initialize 4 variables: first buy, first sell, second buy, and second sell. These will help us track the maximum profit at different stages of the 2 transactions. First buy and second buy are initialized to integer.man_value to ensure we correctly calculate the profit during the subtraction, while first sell and second sell are initialized to 0. Now, we iterate through each price in the input array. During each iteration, we update these variables step by step. First, we calculate the maximum profit after the first buy by taking the maximum of the current first buy and the negative of the current price. This accounts for the cost of buying the stock. Next, we calculate the maximum profit after the first sell by comparing the current first sell value with the sum of first buy and the current price. This effectively simulates selling the stock to realize a profit. Then, we update the maximum profit after the second buy by comparing the current second buy with the profit from the first transaction minus the current price. Finally, we calculate the maximum profit after the second sell by taking the maximum of the current second sell and the sum of second buy and the current price. After the loop completes, second sell will hold the maximum profit achievable from at most 2 transactions, which we return as the result. Here, we start by looking at an example where the prices array is 3, 3, 5, 0, 0, 3, 1, 4. Our goal is to maximize profit from at most 2 transactions. Initially, we set up our variables. First underscore buy and second underscore buy are both initialized to negative infinity because we haven't made any purchases yet. Similarly, first underscore sell and second underscore sell are both set to 0 since we haven't realized any profits. Now, for the first price in the array, which is 3, we calculate first underscore buy as the maximum of its current value, infinity, and negative 3, the cost of buying the stock. This gives us minus 3, meaning we've made our first purchase at a cost of 3. Next, we calculate first underscore sell, which remains 0 because selling at the same price results in no profit. Moving to the second transaction, second underscore buy also gets updated to minus 3, as we simulate buying a second stock at the same price. Finally, second underscore sell remains 0 since selling again at this price yields no profit. At the end of this first iteration, we haven't made any profits yet, but our variables are now set up for further calculations. In the second iteration, the price remains 3, so there are no changes to the values of first underscore buy, first underscore sell, second underscore buy, or second underscore sell. Now, in the third iteration, where the price is 5, things start to change. First underscore buy remains minus 3, as it's still the maximum of minus 3 and minus 5. However, first underscore sell updates to 2 because selling the stock purchased at 3 for a price of 5 results in a profit of 2. For the second transaction, second underscore buy remains minus 3, as it's the maximum of its current value and the new possible buy value of 2 to 5, which is minus 3. Finally, second underscore sell also updates to 2, reflecting the profit from selling the second stock at 5. At this point, we've realized a profit of 2 from both the first and second transactions, and we're ready to evaluate further prices for additional opportunities. When the price drops to 0 in the fourth iteration, we see an update in first underscore buy. It now becomes 0, as this is the maximum between minus 3 and minus 0, meaning we're resetting our first purchase to take advantage of the lower price. First underscore sell remains 2, as no better profit is achieved by selling at 0. For the second transaction, second underscore buy updates to 2, reflecting the new maximum of minus 3 and 2 to 0, which is 2. Second underscore sell also remains 2, as there's no additional profit from selling at this price. In the fifth iteration, the price is still 0, so all values remain unchanged. Now, when the price increases to 3 in the sixth iteration, we see first underscore sell increase to 3, as selling the stock purchased at 0 now yields a profit of 3. Second underscore sell also updates to 5, as selling the stock purchased at 3 gives an additional profit of 5. At this stage, second underscore sell is tracking the best profit from 2 transactions so far. As the price moves to 1 in the seventh iteration, there are no changes to first underscore buy, which remains 0. First underscore sell remains 3, as no better profit is achieved by selling at this price. For the second transaction, second underscore buy remains 2, and second underscore sell stays at 5, as no additional profit is realized. Finally, when the price increases to 4 in the eighth iteration, we see an update to first underscore sell, which becomes 4, reflecting the profit from selling the stock purchased at 0 for 4. Second underscore sell also updates to 6, as selling the stock purchased at 2 for 4 yields a total profit of 6. At this point, we've evaluated all prices in the array, and the maximum profit from 2 transactions is stored in second underscore sell, which is 6. In the second example, the prices array is 1, 2, 3, 4, 5. Starting with our initial state, first underscore by and second underscore by are both set to negative infinity, while first underscore cell and second underscore cell are initialized to 0. For the first price, 1, first underscore by updates to -1, reflecting the cost of buying the first stock. First underscore cell remains 0, as no profit is realized yet. Second underscore by also updates to -1, and second underscore cell remains 0. When the price increases to 2 in the next iteration, first underscore cell updates to 1, reflecting the profit from selling the stock purchased at 1. Similarly, second underscore cell updates to 1. This process continues as the price rises. For each subsequent price, first underscore cell and second underscore cell increase by 1, reflecting the consistent profits from selling at higher prices. By the end of the fifth iteration, second underscore cell reaches 4, which is the maximum profit achievable with 2 transactions in this scenario. In the final example, the prices array is 7, 6, 4, 3, 1, where prices continually decrease. As in previous cases, we initialize first underscore by and second underscore by to negative infinity, while first underscore cell and second underscore cell are set to 0. For the first price, 7, first underscore by updates to -7, reflecting the cost of buying the first stock. First underscore cell remains 0, as there's no profit from selling. Similarly, second underscore by updates to -7, and second underscore cell remains 0. As prices continue to drop, first underscore by updates to reflect the lower cost of purchasing stocks, but first underscore cell and second underscore cell remain 0 throughout, as no profitable selling opportunities arise. By the end of the fifth iteration, all transactions result in 0 profit, and second underscore cell remains 0, indicating no gains were possible in this scenario. In analyzing the time complexity of the solution, we begin by looking at how the algorithm processes the input list of prices. The solution iterates through the list exactly once, where the length of this list is denoted as n. During each iteration, the algorithm updates 4 key variables: first underscore by, first underscore cell, second underscore by, and second underscore cell. Each of these updates involves a simple mathematical operation, such as calculating the maximum of 2 values or performing basic arithmetic, all of which take constant time, or O1. Since these updates are performed once per price in the list, the total work done in each iteration is still O1. Multiplying this constant operation cost by the n iterations of the loop gives us an overall time complexity of O(n). This linear complexity ensures the algorithm is efficient, even for large input sizes. Turning to space complexity, the solution is exceptionally efficient in its use of memory. Regardless of the size of the input, it only requires 4 variables: first underscore by, first underscore cell, second underscore by, and second underscore cell, to store intermediate results. These variables consume a constant amount of space, as no additional data structures are used and no recursive calls are made. As a result, the space complexity is O(1), meaning it remains fixed and does not grow with the input size. Now, let's compare this optimized approach to a brute force method. A brute force solution would involve generating all possible pairs of buy and sell transactions for 2 transactions, iterating over all combinations of indices. This would result in a staggering time complexity of O(n) to the power of 4, which quickly becomes impractical for larger inputs. In contrast, the optimized approach reduces the time complexity to O(n) by using dynamic programming principles. Here, the algorithm tracks cumulative maximum profits for 2 transactions in just a single pass, making it highly efficient. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. Regardless of the arrangement of prices in the input, the time complexity remains O(n), and the space complexity stays O(1). This is because the algorithm processes the entire array and performs the same constant time updates to its variables in every case. There's no variation in computational cost, making the algorithm consistent across all scenarios. To further justify the big O classification, the loop executes exactly n times, performing a constant amount of work in each iteration, which leads to a total time complexity of O(n). Additionally, the fixed number of variables ensures that the space requirement remains constant at O(1). With no additional loops, recursive calls, or data structures, This solution represents an optimal balance between time and space efficiency, making it well suited for handling large datasets. When solving this problem, it's important to avoid some common pitfalls that can lead to incorrect results or inefficiencies. One frequent mistake is neglecting edge cases, such as when the input array is empty or contains only one price. In these scenarios, no transactions are possible, and the profit should correctly return as zero. To address this, make it a habit to check the size of your input at the beginning of the function. Another issue is misunderstanding the problem's constraints. Some might assume that buying and selling must occur on consecutive days or fail to grasp that overlapping transactions are allowed if they follow the rules. Carefully reading and understanding the problem statement is critical to avoid such errors. Additionally, many people start with a brute force approach using nested loops, but this quickly becomes inefficient as the input grows. Instead, focus on optimized methods like dynamic programming or greedy algorithms to reduce time complexity. Lastly, when using recursive solutions, forgetting to reset key variables, such as the maximum profit, between states can lead to incorrect calculations. Always trace through your recursive logic to ensure variables are restored appropriately after each call. Another common issue is off-by-one errors, which can occur when defining loop boundaries. For example, you might iterate one day too far or miss the last day entirely, leading to inaccurate results. To avoid this, clearly define the range of days you intend to work with and test your solution on small, manageable input cases to confirm correctness. From an interview perspective, recognizing patterns is crucial. Many stock-related problems, including this one, share similar structures, so identifying the underlying buy and sell stock pattern can help you quickly determine the most suitable approach. Interviewers often challenge you to improve your solution, so be ready to explain why your chosen method is optimal, especially if you've achieved time complexity. Testing edge cases is another critical step. Situations like an empty array, a single price, or consistently increasing or decreasing prices can expose flaws in your logic. Finally, if you're using dynamic programming, it's important to articulate the trade-offs between space and time complexity. For instance, while storing a DP table may be more space-intensive, it offers flexibility for handling additional constraints. When studying this problem, it's helpful to explore related problems that share similar concepts but vary in their constraints. For example, LeetCode 121 involves a single transaction, while LeetCode 122 allows unlimited transactions. Problem 123, the one we're working on, limits you to at most 2 transactions, while LeetCode 188 generalizes this further to k transactions. LeetCode 309 introduces a cooldown constraint, adding another layer of complexity. Understanding these variations can deepen your grasp of the core concepts and prepare you for different scenarios. In terms of alternative approaches, the single-pass greedy algorithm is a great option for simplicity and speed, as it runs in time. However, it may not work for problems that require multiple transactions or additional constraints. Another approach is dynamic programming, which provides the flexibility needed for more complex variations, such as those with cooldowns or limited transactions. The trade-off here is higher space complexity, as you'll often need to store a DP table to keep track of states. Other techniques, like divide and conquer, can be helpful for breaking the problem into smaller subproblems. This approach can aid in understanding the structure of the solution, but it's generally less intuitive and slower, with a time complexity of n log n, compared to more optimized strategies. The sliding window technique is another alternative that works well for problems with fixed intervals or constraints. For instance, if you had a problem where you could only consider profits within a certain range of days, this method could be highly effective. However, it's less generalizable when the problem involves overlapping intervals, which is often the case in stock trading problems. Each of these methods has its strengths and weaknesses, so it's important to choose the one that aligns best with the problem's constraints and requirements. Great job! To wrap up, we summarized the dynamic programming approach to solving best time to buy and sell stock 3, discussed its key takeaways, and highlighted its efficiency. Thanks for watching. Be sure to like, subscribe, and stay tuned for more coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!